Hello. So we are in the proof of the pointwise ergodic theorem, and we actually finished the pointwise part, but let me remind you of the statement. Theorem by Birkhoff. Let X be mu be a probability space, and T from X to X measure preserving. Let F be an L1 function. Then, when we look at the ergodic averages, we might write AN of F for the averages of the orbits along the orbit up to time n, which is 1 over n, sum j from 0 to n minus 1, f of t to the j x. This converges as n goes to infinity to the conditional expectation of the function with respect to the sigma algebra of invariant sets. And this convergence is almost surely end in L1, where ET is the set of invariant sets. And we already proved the pointwise statement almost surely. Pointwise almost surely is already done. Are there any questions regarding that slightly tricky proof? Better if not, because it would be hard to sort of dive into a detail without doing the whole thing again. So we want to upgrade that statement and also show L1 convergence. Of course, there's only one candidate for L1 convergence. It must be the same function, because if you have an L1 convergence, there's a subsequence to the convergence pointwise, but the pointwise limit without subsequence you already know. So, we also already know the convergence in L2 for an L2 function. And the upgrade from L2 to L1 is rather easy. And that's what I want to convince you of. To prove convergence in L1, we use the mean ergodic theorem. For L2 functions. Let f be our L1 function, let epsilon be greater than 0, and let g be an L2 function that is very close to my L1 function. F minus g, one norm is less than epsilon. Right. We said L2 is contained in L1, contains, of course, all the simple functions, so L2 is dense in L1, and hence we can do that. Okay, that's again F1. For G, we already know the convergence, so we check what's going on. This implies, let's look at the lim sup as n goes to infinity of the ergodic averages of F minus the desired limit, which is the conditional expectation, And then I just throw in the G, right? In the original statement, I don't have the G, but let's throw in the G here and say this is less or equal than the lim sup. So n goes to infinity of an of f minus g. This is one norm. This is one norm. Plus an of g minus p. I think I called it pt in the mean ergodic theorem, the orthogonal projection onto the space of invariant functions. That's pt of g, and originally it's one norm, plus, and then I have pt of g minus e f e t, one norm. Right. It's kind of triangle inequality. I put the an of g in, and I took it also away, right? And I put this ptg in, and I also took it away. Took it away and put it in, and then this is just triangle inequality for the one norm. Now the one norm of f minus g is less than epsilon. If you average something small, it stays small. That's just triangle inequality. And the fact that when you compose a function with t, it doesn't change the integral. We already know that. So this thing, the average here, is always less than epsilon. So I get less or equal than epsilon from this, plus lim sup n goes to infinity of an of g minus pt of g. And now I change to the two norm. The two norm is bigger in a probability space. So I can change from the one norm to the two norm. It's maybe confusing to remember these things, but at some point you will remember this, that for probability space, the two norm is the bigger one, because you can mimic the one norm by taking the inner product with the signature of the function. And the signature of the function is an L2 function, because, yeah. And that's why the two norm is bigger than the one norm. So it's a special case of Cauchy-Schwarz. So I can make this change, and it is fine. This thing, the projection to the space of invariant functions and the orthogonal and the conditional expectation with respect to the sigma algebra of invariant sets, it's actually the same thing, the same operator. So this is plus E G minus F, one norm. And that's zero because of the mean of the L2 convergence for L2 functions. And this is less than epsilon. Because the conditional expectation has operator norm 1. We showed that when we talked about conditional expectation. Yeah, and then since this holds for all epsilons, we are done. Okay, so maybe there's a tiny thing for you to think about, to check that the orthogonal projection operator to the space of invariant functions, as we described it in the mean ergodic theorem up there, or in the discussion last week, and the projection operator to the space of ET measurable functions. Those are the same projection operators. Because being invariant under ET being invariant under T and being measurable with respect to ET are the same thing. Okay, there's a slight issue. We'll get to that. We'll get to that because now I've finished with this thing. So let me talk about this slight issue that would pop up if you think about it very carefully. So, yeah. Okay, let me write down the issue because I should isolate the thought that I have, and then we'll show that it's not an issue. In the proof above, the following was used for F in L2 to be invariant under UT, under this operator that we get by composing with T, i.e. UTF equals F in L2, it is equivalent to say that modulo mu, or that is a representative of F. F is, strictly speaking, an equivalence class that is ET measurable. So there's a little bit of null set issues here because that thing is an equivalence class. UT is, when we talk about L2, we talk about the equivalence class, and then UT is defined on the equivalence class. So UTF equals F doesn't strictly speaking mean F composed with T is F pointwise everywhere. It doesn't mean that. It just means F composed with T is equal to F almost surely. But when I say I can find a representative of F that is actually ET measurable, then this well-chosen representative will have F composed with T is equal to F everywhere, not just almost everywhere. And I'm saying these two things are the same thing. But let me just do this on the set level of sets, because one can define another sigma algebra, which at first sight would be bigger than this ET, but in hindsight it's more or less the same thing. Yes, it's bigger, strictly speaking, but if you ignore null sets, it doesn't matter whether you ignore them on the left or you ignore them on the right somehow. That's the kind of lemma that I'm doing. Lemma. Recall ET is up there. It's the set of all B's for which T inverse B is equal to B, where in the definition of the sigma algebra we don't see the measure. Define ET comma mu to be the set of all B in B for which T inverse B is basically the same thing as B. So the symmetric difference of T inverse B and B has measure 0. Then, obviously, ET is contained in ET comma mu. And let me, already use the notation mod mu. So I write equality with a mu underneath. They're the same thing anyway. And so what's the definition of the symbol? Definition, let A and C be two sigma algebras. We write that A is contained in C mod mu if for any A in A there exists a C in C with mu of A symmetric difference to C is 0. Moreover, A is equal to C mod mu if A is contained mod mu in C and C is contained mod mu in A. Yeah, so it's mod mu inclusion, mod mu equality. Usually one isn't so careful about null sets in ergodic theory because they're just null sets and they appear naturally because the ergodic theorem is only telling you something almost surely. So every time you apply the ergodic theorem or even Poincaré recurrence, there will be null sets around and you just keep ignoring them and it's okay. And the lemma sort of helps to justify why you can ignore them. You could have thought maybe that there are two different notions of invariant sets, and yes, there are two different notions of invariant sets, but if you ignore null sets, they become the same again. Okay. Proof. I want to show that ET mu is mod mu contained in ET. Let A be in ET mu so that the mu of T inverse A symmetric difference with A is equal to 0. And I want to define out of this A, I want to define a different set that's not so different. I'm only allowed to change it on a null set, so that the new set is strictly invariant. And it's just a nice trick. I mean, in a sense, we already played with this trick in the proof of Poincaré recurrence. So we're allowed to recycle ideas. We define A twiggle to be the intersection over all k from 0 to infinity of the union from j equal k to infinity of t to the minus j a. It's kind of a limb soup. You could call this the limb soup of the orbit of the set. But if you don't want to call it that, it's also fine. Just that's our definition. And this set is basically A, right? T to the minus j is basically A. Apart from a null set, it's A. So if you have countable many sets that are basically A, and you take their union, countable unions and null sets behave very well. You get a set that's basically A. So this thing is up to a null set equal to A, independent of which k you're using. So if you now intersect sets that are all basically A, and you have countable many of these, you again collect null sets, then this thing is basically A. So up to null sets, we have t to the minus j A is A, union j from k to infinity, t to the minus j A is A, and A twiggle is A. That one could write more down, but the idea is still the same. A tilde symmetric difference A will be equal to 0. So it's a version of A. But what's nice about A twiggle is if I just take the pre-image of it, I can pull the pre-image in, get t to the minus j minus 1 here, moreover t to the minus 1a twiggle is equal to union at intersection k from 0 to infinity, union from j equals k to infinity, t to the minus j minus 1. So that creates a shift in the index here, right? So I can write it down again, k equals 0 to infinity, intersection j equals k plus 1, t to the minus j a, which again creates a shift. So it's like taking the intersection from 1 to infinity. But the union here is decreasing. So whether you take the intersection of the first set and the second and the third and so on, or just take the intersection of the second, third and so on, will not make any difference. So this is the original set 8 tilde, and that's what we wanted to prove. That for any mod mu invariant set, this is mod mu invariance, I can find an honest set that's honestly invariant, 8 tilde, so that the symmetric difference between the old set and the new set is 0, has measure 0. Yeah, and I think maybe I state the lemma that claim gives you this thing here and leave it for you to check. If f in L2 mu satisfies f composed with t equals f almost surely, so as an equality in L2 space, then there exists a representative f twiggle of L2 mu, so that f composed with t equals f everywhere. Let's just talk about it a bit. I don't want to write anything down. If f is a characteristic function, you just apply the lemma straight away, right? If f is a characteristic function, the set that you applied, that you got, or for which you looked at the characteristic function, that set needs to be in ET mu. But because of what we just proved, this set has a different version, a different representative that is strictly invariant. Just take the characteristic function of the other guy. If you have now a general f, you could approximate it by a simple function from below. Say f is positive. You do the positive and negative part separately. It's always the same in measure theory. So just think of a positive f, and then look at a simple function below that you really define using f. How do you really define it using f? You just take pre-images of intervals in the reals, use the lower bound of the interval as the value, and take the corresponding linear combination. Right? That's the standard thing. If you have some kind of function, you take this approximation where you take the interval in the target, which is the reals, to define B1, B2, and so on. And then take the lower bound of the interval as the value of your simple function in the pre-image. Because your original function was invariant mod mu, when you define these pre-images, these sets will be invariant mod mu. So these sets you can replace by something that's equivalent and would be strictly invariant. So you would get a simple function that's strictly invariant and is below your function almost surely. And then you take the pointwise limit, the increasing limit, and you get a strictly invariant function because it's Point was limit of strictly invariant functions. You have a question, yes? Yes, F tilde, thank you. The board didn't move, yes. Good. So I'm not writing something down, but I drew a picture. That's good enough. Okay. I think we are long overdue a definition. Definition, let X be mu, be a probability space, and T from X to X, measure preserving. We say that T is ergodic if mu of T inverse B, symmetric difference B, equals 0, implies that the set itself is not interesting. That the measure of the set is 0 or 1. That the measure is a null set or a co-null set. So for any measurable set, we should have that B in B and the measure, the B is almost invariant, or by the previous discussion, you could also say here, B is strictly invariant, it wouldn't change the definition. An almost invariant set or a strictly invariant set is never interesting, has measure 0 or 1. If that's the case, then the transformation or the measure, again, depending on the context, maybe it's the measure that is ergodic or the transformation is ergodic. Yeah. So that's an irreducibility criterion somehow. It's saying that our measure can't be chopped into two invariant pieces. And in this way, it's kind of a nice notion. In topological dynamics, we kind of had two irreducibility definitions. We said topologically transitive is a good thing, but minimality is also a good thing, and it's not quite clear which one is the better one. Here, that's completely obvious. That's the right one. There's only one, and that's the one, somehow. That's the irreducibility condition in ergodic theory. Good. Maybe it's good to have a corollary of the ergodic theorem under the assumption of ergodicity, just to see what this notion would mean in the ergodic theorem. And it doesn't matter whether you take the mean or the L1. It's all about identifying what the limit is. And usually the limit is difficult, right? We need to do an orthogonal projection or a conditional expectation. Could potentially be difficult. But if you're ergodic, no questions asked, the limit is very easy to identify. Corollary, let X be mu T be ergodic on a probability space. Let F be in L1, then the ergodic average converges to integral F d mu, almost surely, and in L1. And if your F is L2, you also have L2 convergence, because that's then the case of the mean ergodic theorem, which we also understand. Proof. If F is in L1, then EF given ET is an invariant function. Hence, for any interval in the reals, the preimage B F inverse, preimage of the interval, which is now a subset of X, is invariant. But invariant functions cannot be interesting. That's our definition of ergodicity. By definition of ergodicity, this gives mu of F inverse of the interval is 0 or 1. So we have a function on a probability space, and for any interval in the reals, when we take the preimage, we either get a null set or a co-null set. Such a function is constant, almost surely. A function like this, any function with this property is constant. Where again, we need a bit of measure theory to argue for that. Yes?
Shouldn't on the right-hand side the f's be replaced by the expectation of f with respect to...
Yes. Thank you. Thank you. That's very important. But I'll can only squeeze in a tilde. So I put here tilde. Thank you. I'll not write down it in all of its detail, but I'll just give you the idea why it's true. So first of all, you decompose your reals into countably many intervals, say of length 1. All of the preimages of any one of these intervals will have measure 0 or 1. But of course, 1 you can only get once, because the main of definition is a probability space. So we get one of these intervals contains almost all of the values. The remaining intervals are not important. And then you do the same thing with this one. Maybe you just, n plus j over L, n plus j. Again, it's a disjoint union. N plus j plus 1 over L, where your disjoint union goes from j equals 0 to L minus 1. One of these smaller intervals, or maybe one of these smaller intervals will have measure 1. The remaining ones will not be important. Maybe you let your L be a power of 2 and just look more and more for the right value. And you will get, in the end, you will have the correct value. If L goes to infinity, you will find the correct value, and then the function will have to be constant, equal to that value. Don't write down anything. I think the idea was kind of obvious if you practice your measure theory, which you should. So there's something to be said here. And maybe that also goes back to the history of the subject. So this is the ergodic average. We call this the ergodic average, and we said in the definition that this is an average over a piece of the orbit. So you could say this is the time average, right? Because you sum over a piece of the orbit and you divide by n. So this is a time average. On the right, we have the space average. So the statement of the ergodic theorem in the ergodic case is that time averages converge to space averages, which is, yeah, nice catchy phrase. And it's also where the whole terminology and the ideas come from, because I think it was Boltzmann who had this Ergoden-Hypothese. Excuse my German, he was from Vienna. So, ergodic hypothesis, which said precisely this, that if you have kind of this particle moving around with Brownschen movement, whatever, in something, then it will get everywhere. And that was a bit too vague and a bit asking for a bit too much. He was a physicist. But it gave mathematicians the right ideas, and then they tried to figure out what could possibly be the true mathematical statement behind that, and the whole subject was born. And this is, yeah, a nice conclusion. And of course, ergodicity, for this conclusion, ergodicity is absolutely necessary. Because if you have a space, and this is your space, but secretly, your space consists of two blobs and not one blob, and the transformation is moving the left thing around and moving the right thing around without mixing those two things. You can't possibly hope for that, right? For all functions, almost surely, because just take the characteristic function of the left and start on the left, and you get the measure you get 1. If you start on the right, you get 0. But if both sides have positive measure, yeah, we definitely don't have this conclusion here. So ergodicity is a necessary assumption for this stronger conclusion here. Okay. I think this we already understand, but let me still say it. I think it's a version of, yeah. Ergodicity is a unitary property. It's visible for the unitary operator, well, which is sometimes not a unitary operator, for the isometry, for the Koopman operator. So the Koopman operator knows whether the system is ergodic or not. That's what I wanted to say. There are many other characterizations of ergodicity, and maybe we'll see some of them. But, yeah. This one is kind of fitting with what we discussed right now. X p mu t is ergodic if and only if ut, which is a map from L2 back to L2. Depending on the context, sometimes it's a map from L2 to L2, sometimes it's a map from L1 to L1. But it doesn't matter for this lemma. It would also be true with L1. If this operator has only a one-dimensional eigenspace for eigenvalue 1. It always has one eigenvector, the obvious one, meaning just a constant function, say. Constant function 1, if you compose the constant function with t, you get a constant function, the same one. So you always have this one eigenfunction, And if there's no other eigenfunction than this one, then the system is ergodic. If and only if. Proof. If T is ergodic and F composed with T equals F almost surely, then F has, we talked about that before, has a representative with F composed, let's call it F twiggle. F twiggle composed with T is F twiggle, and ergodicity implies F equals F twiggle equals constant almost surely. So that's one direction. If UT has only a one-dimensional eigenspace for eigenvalue 1, and B equals C inverse B is measurable, then F equals characteristic function B is an eigenfunction for eigenvalue 1, which implies that F must be a multiple of the constant, and F is equal to the characteristic function is equal to some constant times the constant function on the whole space, almost surely. And if we now take the integral, say, on both sides, we see that the measure of the set is equal to C. But if C is also the value that the characteristic function takes on almost surely, then C must be 0 or 1. So the measure of the set must be 0 or 1. Okay. Yeah. When the subject was born, functional analysis wasn't developed to the state it is developed now, of course. But I think people really liked and understood that these Koopman operator, these potentially unitary operators, are a useful tool for studying ergodic theory, and they became very important, of course, in the time in between. And people were kind of trying to do everything with them. And hence the question always comes up whether this or that property is a property that we can see and study using this unitary operator, or the Koopman operator. And ergodicity is definitely a thing that we can see from studying only the unitary operator because of this lemma. We'll see other properties, but probably we'll also see some properties that can't be discussed using the unitary operators alone. Okay, so maybe we want some, after the break, we want some concrete examples of ergodic systems. Good, we are all eager to see our first ergodic systems example, except that we already saw them, but never mind that. TP from the torus to the torus, x goes to px, of course, mod 1, for p greater equal to an integer, is ergodic with respect to Lebesgue. Okay, and we just discussed this lemma that says that ergodicity is a unitary property. So I can switch to L2 and think about L2 functions and whether the L2 functions are eigenfunctions for composition with T. That's what we are going to do. So let f in L2 of the torus, but we also said that before that for the Lebesgue integration, there's no difference between the torus and the 0-1 interval. Closed or not closed also doesn't matter for Lebesgue integration. Satisfy that UTPF equals F. And from that formula, from this equation, we want to conclude that the function is a constant function. So what do we do? What could we use? Yes? Yes, Fourier analysis is the tool, and that's also the reason why I tried to push sort of the ergodic theory a little bit further into the semester, because some of us already only learned this word last week. So now I'm happy. Fourier series, yes. Let f be the sum over all n in Z, Cn some coefficient, En the standard orthonormal basis for L2, where En of x is e to the 2 pi I nx for x in 0, 1. Again, it doesn't matter whether you read this as closed or not closed, intentionally cryptic. So I'll know my function can be represented by this series, and now I use my definition of composition with TP and calculate both sides. Therefore, UTPF is equal to F composed with TP is equal to the sum of n in Z, Cn, En of Px. But what is En of Px? I multiply the x with P, but that's the same thing as multiplying the n with P. So I get NP of x. So I get that the sum over n and Z, Cn En, is equal to the sum over n and Z, Cn ENP. Where the Cn's are the Fourier coefficients, and these are the En's are the functions. And that's a bit funky now, because on the right-hand side, we only see Fourier coefficients for those n's that are divisible by p. If the n is not divisible by p, then the corresponding Fourier term doesn't appear on the right. But on the left, it's supposedly appearing, because here we summed the unknown general function f in L2 over all the phases that are possible. But Fourier coefficients and Fourier expansion is unique. So the infinitely many equations in this one equation hiding. So in particular, this is saying that if the n is not divisible by p, the Cn must be 0 because it doesn't appear on the right-hand side. This implies Cn is equal to 0 if p does not divide n. Maybe I write it down. The corresponding En does not appear on the right. So must have coefficient equal to 0 on the left. So let me just draw sort of the Fourier coefficients of sorts. So I have here a line, and here somewhere I have the 0th entry, the 1 entry, 2 entry, and so on. Then somewhere I have the pth entry, and so on, -1, and so on. And what I'm saying is that of all every integer had a coefficient, but no, these guys, they're all 0. The corresponding Cn, they're all 0. These guys, the corresponding Cn, are all 0. Now the remaining one is the Cp coefficient. There's one coefficient here. What do I do about this guy? Well, I have a formula for this guy as well. Namely, it is a coefficient that appears on the right as well. Right? So that's why I don't yet know that the Cn is equal to 0. But what is it equal to? What is the Cp equal to? On the right it appears, but with which coefficient? I need to upgrade my stakes. Aha, you already got one today, right? Oh, sorry. No, I meant you, yes. Yes, thank you. So Cp is equal to C1 because when n is equal to 1, I have C1 EP. That's the only place on the right where EP is appearing. And on the left, yeah, it's CP EP. So Cp must be C1. But C1 is already a coefficient that I know is equal to 0 because 1 is not divisible by P. So actually, I can repeat this argument infinitely many times. It doesn't matter how often the integer is divisible by P. I can reduce it until it's not anymore divisible by P. There's only one counterexample to this. If my n is 0, I can divide it by P infinitely many times. But I'm not trying to show that C0 is 0, because C0 is the coefficient for the constant phase. So the only thing that's left is the C0 term. All the other terms are 0. By repeating the argument, we obtain Cn is equal to 0, except when n is equal to 0. This shows f is equal to C0, E0 is equal to C0 constant function is constant. Yeah, I think that's good enough. Okay, so that proves ergodicity, right? We took an arbitrary L2 function with the invariance, applied Fourier series, analyzed what it means in terms of the Fourier coefficients, and got down to the point where the only Fourier coefficient that is allowed to exist is the 0 Fourier coefficient, so the function must be constant. Since this is true for every invariant function, the system is ergodic. Corollary conclusion, therefore, for almost every x in 0, 1, we have if I write the x as 0.a1, a2, a3, and so on in base p, then the limit as n goes to infinity of 1 over n, the number of times, number of j's from 1 to n with aj is equal to 2, whatever, some digit, it doesn't matter which digit, is equal to 1 over p. And it doesn't matter which digit I do here. If I do a 0 or a 1 or up to p minus 1, I could write this down for any of these digits up to p minus 1. I will always get that the limit is 1 over p. Why? This follows from the ergodic theorem. In the ergodic case, see corollary, by using a characteristic function. I highlighted that case 2, so let me write down the characteristic function in that case. I take the characteristic function of the interval 2 over p, comma, 3 over p. Because that interval corresponds to the first digit after the comma being a 2. And when I apply my dynamical system, apply p, multiply by p, we have discussed this, the digits shift along. So by asking whether the characteristic function for tx is 1, I'm asking whether the second digit is equal to a 2, etc., etc., etc. So the ergodic sum is really just counting how often I see in the digit expansion the prescribed digit. And the ergodic theorem tells me that asymptotically, the time average, that's the time average, equals the space average. The space average is, of course, just the integral of the characteristic function. The interval has length 1 over p. So I get 1 over p. We can repeat this also for finite words. Right? Currently we looked at just one digit at a time, but we can also look for 2024 appearing somewhere in the base P expansion and ask how often this happens. How often do we see 2024 appearing in the base P expansion? If we keep looking to the right, it's, of course, 1 over p to the 4 many times, almost surely, because only the length of the word matters, because the length of the word determines the length of the interval that I will see. A number is called normal base P if this is true and this is also true for all finite words. And the ergodic theorem is saying almost every number is normal in base P. But of course, P is just an integer, so we can also vary the integer. And we can ask for a number to be normal in every base. So almost every number in the interval will actually be normal in any base. In base 10, in base 5, in base 17, it doesn't matter. In every base it will be normal, almost surely. It's great, except we don't really know a single example that satisfies this. Probably P satisfies this, or square root 2 or something. Nobody knows. But almost every number will satisfy it. No questions asked. Good. I'm not writing this down, it's just a game. Let's do another example. Well, on the torus we had another thing, like rotation by alpha. And of course we need to separate the rational from the irrational case. And the rational creates periodic points, creates many periodic points. It's not ergodic. No, definitely not. So we are only interested in the irrational case. R alpha from the torus to the torus, x goes to x plus alpha for alpha not in Q is ergodic. Let f in L2 be invariant. Then f is equal to the characteristic to the Fourier expansion Cn En, n in C. But that's also f composed with R alpha, which is f of x plus alpha, which is sum of all n and z, Cn En of x plus alpha. But what is En of x plus alpha? En of x plus alpha is either the 2 pi I x plus alpha, no, n times x plus alpha. So I get either the 2 pi I n alpha, either the 2 pi I nx, which is my En of x. So if this is equal to f of x, which is what the invariance is asking, I get that the sum Cn e to the 2 pi I n alpha En is equal to the sum over all n Cn En. This time I have all phases as all frequencies appearing both on the left and the right. But on the left they appear with this extra factor. On the right they just appear as Cn. But Fourier coefficients are uniquely determined by the function. So whatever that is, it needs to be equal to that thing for every n. Cn e to the 2 pi I n alpha is equal to Cn for all n in Z. We haven't used yet the assumption that alpha is not rational. If alpha is not rational, n alpha is not an integer. Except the case, again, for a silly case. When n is equal to 0, n alpha will be 0, that's an integer. But for n not equal to 0, n alpha will not be an integer. And if n alpha is not an integer, then e to the 2 pi I n alpha is not 1. So this is not 1 for n not 0. But if I multiply a complex number by something that's not 1 and it stays the same number, there's only one way to solve that linear equation. The Cn must be 0, except possibly for n equals 0, which is precisely what we wanted to show. Cn is equal to 0, except possibly for n equals 0. Therefore, f is equal to C0 constant function is constant. This shows that R alpha is ergodic. This worked so well. Let's just do it in any dimension. Example, high dimensional rotation. Let alpha underlined be alpha 1 up to alpha d be a vector, a d-dimensional vector. We define R alpha, which is a map from the t-dimensional torus to the d-dimensional torus, which sends an x to x plus alpha. The x is also underlined, the alpha is also underlined. So I'm adding alpha 1 in the first coordinate, alpha 2 in the second coordinate, and so on and so on. And I'm asking, when precisely is R alpha ergodic with respect to Lebesgue measure? Lebesgue measure is preserved, that's an easy thing, it's just translating the cube around, so that's not surprising. Lambda equals d-dimensional Lebesgue. Is preserved, is invariant. When is it ergodic for R alpha? And to some extent, we don't really need to know the answer already. We just start the machine. We just start the Fourier machine. And at some point, we see something of importance to us, and we'll analyze it then. And then we will have a proof already. So let's just do it. Suppose f is equal to f composed with R alpha. So our f, our original f, is again the sum over Cn En, where the n is now allowing different phases in different directions, and the phases are all integers, so I'm summing over c to the d, because I'm in the d-dimensional torus. And the En, this basic oscillating function on the d-dimensional torus, is just e to the 2 pi I, and then I take the inner product of the n with the x. The n is an integer and the x is more than integer, so the inner product is only defined up to an integer, but that's not a problem because e to the 2 pi I times an integer is 1 anyway. I don't care about that. Right, it's n1 times x1, n2 plus n2 times x2, etc. And now I compose this with alpha, and it's kind of similar to the calculation up there. So f is supposed to be, just write down the equation. Sum n is in Z, d, Cn, En, that's my f, is supposed to be equal to the sum n in CD, Cn, En composed with R alpha. So I need to calculate what this En composed with R alpha really is. En of x plus alpha It's not surprising. I just write down the answer. It's e to the 2 pi I n1 alpha 1 plus nd alpha d times en of x. So let me change this and just write the scalar again. E to the 2 pi I n1 alpha 1 plus nd alpha d en period en. So composing with the rotation, the d-dimensional rotation, will again change the Fourier coefficients by this factor. But the Fourier coefficient is not allowed to be changed if we want to prove ergodicity. So what we need for the alpha is that this factor is only in one trivial case equal to 1. In all other cases, it should be not equal to 1, and then we win. If it's ever equal to 1 in a non-trivial case, we have also found an eigenfunction. Then we just take the corresponding en, and the en will be an eigenfunction, which is not constant. And then there's a bit of a question to see what's the right language to capture the desired property. And without further excursion, I'll just tell you the statement, which we already proved. But what's the statement? With this, we see that R alpha, or the Lebesgue measure, is ergodic if and only if 1, alpha 2, those are d plus 1 numbers, are linearly independent over Q. So we just need linear algebra to phrase the precise condition. But it's linear algebra over Q. Those are real numbers. The real vectors, the vector space R over Q has, of course, infinite dimension. So there are lots of choices of alpha 1 up to alpha d so that this condition is satisfied. Like you could take square root 2, square root 3 would be perfectly fine. If you rotate in the first coordinate by square root 2 and the second coordinate by square root 3, perfect. Or rotate in the first coordinate by e and the second coordinate by pi, perfect, it works fine. Don't rotate by square root 2 and by square root 2, because then you rotate along the diagonal, and then you will rather quickly find invariant sets or invariant functions. But as long as you do sufficiently different things in all coordinates, and that's precisely the condition that you need, you will have ergodicity. Okay, I'll say it again more slowly, why we are actually done, and we did prove the statement. Suppose your alphas satisfy this condition. Then you take your invariant function, go for the Fourier coefficient stuff and get this equation, right? And then you look at this exponent here. And if n is 0, you're happy, you don't need to worry about it. That's the constant function. But if the n is not 0, then and the factor here is equal to 1, then this parenthesis in the exponent will be equal to an integer. Because e to the 2 pi I watt is equal to 1. The watt needs to be an integer. So the parenthesis will be equal to an integer, but if the parenthesis is equal to an integer, you get a contradiction to that statement. So the constant is kind of hiding in the e to the 2 pi I function here. But yeah, that's the statement you get. Let me phrase a lemma that's true in the high-dimensional version, but also true in this version here. Obviously, it's just a special case. And talk a bit about how we could prove this. I see two proofs now that we can equally well do. But what's the statement? Let's go with the high-dimensional version. Why not? Suppose 1, alpha 1, alpha 2, alpha d are linearly independent over Q. Let f be a continuous function on the t-dimensional torus. Then an of f, which we understand what it is, converges to the integral of f d lambda. We already know that, right? Because it's ergodic, and in the ergodic case we converge to the integral. Everywhere. Well, that we didn't know. So the ergodic theorem told you on almost everywhere, right? There's a big difference. As in the discussion of normal numbers, I told you that we can quickly prove that almost every number is normal in every base, but we can't really give one example. Here the situation is different. It's not an almost everywhere statement, it's an everywhere statement. Every point satisfies the correct thing at the cost of using a beta function, right? Don't screw around with L1 functions if you want to prove an everywhere statement. Because of course you can mess up the function very easily on an orbit. It would still be an L1, didn't change the function, right? So how could we prove this? There are two ways at this point that we can prove this. Again, I'm upgrading my stakes. It's a black one. Who has an idea how we could prove this? Yes? So the question, or the possible answer was using density of L1 functions in continuous functions. Continuous functions are completely contained in L1. So we don't need a density. They're sort of, and we are not trying to prove a beta statement for L1 functions, so I don't see how we can use this density. Yes, so in particular also for a continuous function, because a continuous function is L1. The issue is that we don't have we only have an almost everywhere statement. How do we get from the almost everywhere to every point? So the function is fine. We just take one continuous function, apply the pointwise ergodic theorem, say. But how do we get then from the one function, or from the one function and almost every point to every other point? Yes, but we don't have two continuous functions. I don't see how we can use that. Yes?
So statement when it converges uniformly, and then you have the statement.
Yes, so that's a very good approach. Thank you. You also want a black one? No, it's okay. Yes, that's a very good approach because, and it crucially uses something. It uses a crucial property of our rotation, which we also discussed already in topological dynamics a little bit. Namely that the rotation is an isometry. It doesn't mess up distances. So if you take your continuous function and some epsilon, then the function will be uniformly continuous, so there will exist some delta. The same delta will work for the rotated function, for f composed with the rotation. For all of the rotations it will work. So the same delta will work for the average. And that's the word you didn't say. The collection of the averages is equicontinuous. So it's not just uniformly in the space, it's only also uniform in the parameter n. And if you have equicontinuous functions, then a pointwise limit is also a uniform limit. And for this pointwise thing, you don't need pointwise everywhere. You only need a dense set of points where you would converge, and then you already converge uniformly. So that's one method how you could actually prove this as a corollary of our ergodic theorem. There's a second method that's even more direct somehow. You could just study a phase function, an En. Let f be En and figure out what the ergodic average looks like. Let's do that. Let us start with f equals En. Then the ergodic average, let's say maybe this is an Em. Ergodic average of Em at x is 1 over n sum from j equal 0 to n minus 1 of the e to the 2 pi I. And then we have x plus j times the alpha. Right, but look at it, it's just, again, we did that before. This is e to the 2 pi I, mx times e to the 2 pi I, m alpha jth power. That's called a geometric series, right? So we get 1 over n. The e to the 2 pi I mx can just come out. It doesn't depend on j. And then we have the sum, j equals 0 to n minus 1, q to the j, for q equals e to the 2 pi I m alpha. Yes? That's not equal to 1, except when our m is the 0 vector. Again, because of our 1 alpha 2 up to alpha d being linearly independent over q. So we have a formula for this. E to the 2 pi I mx, 1 over n, q to the n minus 1, q minus 1. This could be huge, right? Because q could be close to 1. But it doesn't matter because it can only be huge, sort of, it would be huge, but maybe uniformly in n. It can't be growing in n. It's bounded with respect to n because only the denominator can make it large. Q has absolute value 1. So q to the n doesn't bother us. Q minus 1, maybe, but not after we divide it by n because it's an average we're looking at. So this converges to 0, which is the integral of our function. So it's true for the standard phase functions, standard oscillating functions. But then it's true for sums of such functions. Sums of such functions are called trigonometric polynomials. So it's true for trigonometric polynomials. But trigonometric polynomials are dense in the space of all continuous functions. And you can use that to then get a statement for all continuous functions. After this, the statement holds for trig polynomials. And using Stone-Weierstrass or some other trick, also via density, an approximation argument, an approximation. It's a standard 2 epsilon argument for any, maybe it's 3 epsilon, for any f in C of t to the d. It's not the first and not the last example where somehow you have a choice of different methods. One maybe a bit more ergodic, maybe a bit less quantitative, one a bit more harmonic and more quantitative. So ergodic theory has quite often this downside that it's a bit less explicit about errors. The second proof we can very quickly make into some, we can actually estimate the errors very well because for the character we really have a formula that we can write down and we can estimate the error. And if we have a smooth function, we can also estimate the error very concretely. It's not difficult. In the other argument that we sort of hinted at, using the Ergodic theorem as an input, we don't start with any error, and so we will not get an error statement, an estimate for the speed of convergence. Never mind. I mentioned Benford's law some ages ago, and the rotation is actually the thing that you need to discuss Benford's law for powers of 2. So if you're interested in, say, powers of 2 and powers of 3 simultaneous, and you want to know how often the leading digit of 2 to the n is a 1 and the leading digit of 3 to the n is a 1 simultaneously, you would look at the rotation where alpha 1 is log 2 over log 10 and alpha 2 is log 3 over log 10. And let's just go back down to the one-dimensional case. 2 to the n starts with 1 if and only if we take the logarithm of 2 to the n. That's also called n times log 2. Belongs mod 1 to the interval 0 log 2 over log 10. There's some classical phrases that people have forgotten. Mantisse and abscisse, maybe, something like that. Just referring to the absolute value, no, to the leading, to the integer part of the logarithm, which is just telling you don't know whether the phrases were correct. Never mind, because we have forgotten. One phrase really refers to the integer part of the logarithm, which tells you the number of digits before the comma. And the fractional part, when you just look at it mod 1, will tell you the digits, but not any longer the magnitude. How big it is, you will have forgotten because you took it mod 1. So when you look at 2 to the n and you are asking questions like, what's the leading digit? You should take the logarithm, which is now a rotation instead of a multiplication, but you take the n log 2, you take that mod 1, because you ignore the order of magnitude. And then you just need to know how long this interval is for the Lebesgue measure. Okay, there's an extra step. Is the characteristic function of this a continuous function? It's a characteristic function. Of course, it's not a continuous function. But the statement up there also holds for this characteristic function. So there's another approximation statement that you want to make. The statement up there will hold for any Riemann integrable function. Not for any Lebesgue integrable function, because you can screw up a Lebesgue integrable function on an orbit, right? But if you try to do this for a Riemann integrable function in a serious manner, you will destroy the Riemann integrability. So if you know a bit of analysis about how you can approximate a Riemann integrable function using continuous functions from above and below, it's a nice exercise to prove Benford's law as a corollary of the thing up there. Thank you.